Hi, in this session we are going to continue talking about real numbers, and we are going to look at advanced operations part 2. We talked previously about what was the power with integer exponent, and now we are going to go a little bit deeper into this. The objectives are to introduce the concept of nth root of a real number, and in the same way of the powers now not only with integer exponent but also with rational exponent. The requirements are simply the previous units to handle well the real numbers and their operations, and the concept of power with integer exponent. As we said in the previous sessions, the properties of product, mainly the product operation, allows us to define more sophisticated operations than the multiplication and the addition, and in particular we defined in the previous session what was the power of a number, for example 2, to an integer exponent, in this case raised to 5. In this unit we are going to focus on the inverse question, which is whether we can do it the other way around. Given 5 and 32, ask ourselves which number to raise, which number would have to be raised to 5 to give 32. That is the concept of the fifth root of 32, to what number it would have to be raised to 5 to give 32. We know it is 2 from the previous account and from the account we have here. The fifth root of 2 raised to 5, the 5 and the power. The fifth root and the fifth power go away and only 2 remains. That is, 2 is the number that raised to 5 gives 32. Well, that is simply the definition of the nth root. Instead of the fifth root, we can consider the fourth root, the sixth root, the eighth root, and in this case for us the n is going to be a natural number, not an integer, but a natural number. Thus we can effectively consider the second root, the third root, the fifth root, the eighth root, and so on. However, this definition has problems and will not always exist. First of all, the notation that we are going to use is the one that we used before. Let's talk about the nth root of a, and it is, I repeat again, the number which when raised to n gives us uppercase A. The problematic condition is this: when n is an even number, the uppercase number has to be positive. That's because even powers always give positive numbers. Therefore, we can't find the square root or the fourth root of a negative number. Let's see some examples. For example, the fourth root of 16, we know that 2 raised to 4 gives 16. So the fourth root and the 4 are simplified, and I am left with 2. The fourth root of 16 is 2. The fourth root of minus 16 does not exist. Notice that it is not minus 2, because minus 2 raised to 4 gives 16 again. So there is a big problem here. The cube root of 8, we know that 8 is 2 to the cube, and therefore the cube root of 2 to the cube goes away, and we would be left with 2. The cube root of minus 8, by comparison with the second, does not give any problem. The odd roots do not give any problem, because in fact minus 2 cubed is indeed minus 8, and therefore the solution of this cube root is minus 2. The simplest way to do this type of operation is to handle roots as exponents. Thus we denote the root exponent of n, which would be the nth root operation, as the exponent 1 divided by n. So the square root of 2 is 2 raised to a half. Introducing this notation allows us to simplify quite a bit the nth root of a number raised to another number. Here we are already complicating the question a little. We put an exponent and a radical, but still with this new notation we can reduce everything to a little number, to a raise to an exponent. And now the exponent is no longer an integer, now the exponent is a rational number. Well, fortunately the properties that we had for powers of integers still hold for fractional numbers, for rational numbers. So when we find roots, a fourth root, a fifth root, we will go to power notation, and we will use the properties of powers, which are very simple to use. I remind you again of these properties. We have on one hand, in the first column, in the blue column, we have the operation properties when the bases are equal. If the bases are equal and we are multiplying, the exponents are added. That would be the first one. If we are dividing two powers with the same base, the exponents are subtracted in this order, the one above minus the one below, And if we have a little number raised to a power and raised to another power, as we had seen, what we have to do is simply multiply the exponents. In column B, what we see is what operations, what properties are fulfilled when the bases are different, but the exponent is the same fractional number. In this case, as it happened when the exponents were integers, what we do is simply to take a common factor. We group the bases, a and b, and put the exponent as the common factor. In this case, a times b raised to m divided by n. The same with the division. A raised to a fraction divided by b raised to the same fraction. We put together a divided by b and raise it all to the same fraction. Well, that's all. What have we seen in this unit? We have introduced the concept of the nth root of a real number, and we have studied the basic rules of calculating rational exponents. Some questions to think about. What is the meaning of the number 2 raised to the root of 3? We are raising 2 to an exponent that is not a rational exponent. We have given meaning only to the calculation with a rational exponent, and root of 3, which we know is not rational, is an irrational. It is a real number, not rational. An interesting way to check this, as you know, is to use the calculator. If you have a scientific calculator, you can enter 2 raised to the root of 3 and check what value you get. What value do you get? Is it a real number? We'll see. Thank you.